Welcome to the ESA Junior Faculty Webinar Series, everyone. Sadly, this is our last webinar. We've had a blast with fascinating presentations and discussions, and I would like to thank all of our presenters, discussants, and of course participants for all of your support and engagement. I don't want to take too much time because we have two more amazing presentations and discussions lined up today. Our first speaker is Margaret Samahita. Margaret completed her PhD at Lund University in 2017, and then she did a postdoc at the International Institute for Industrial and Environmental Economics. Currently, Margaret is an assistant professor at the School of Economics at University College Dublin. She is also an affiliated research fellow at the Geary Institute for Public Policy. Her research looks at how decision-making is affected by factors such as image, mood, and self-control, and she also studies how information shapes political preferences. Today, she'll be presenting us her study, Pessimism and Overcommitment. Margaret, whenever you're ready, take it away.
All right. Can you see my screen okay?
Yes.
Yes.
Perfect. Thanks, Pilar, and the rest of the organizers. So today's paper is joint work with Toussaert, who's hopefully also here to answer any questions that might arise during the presentation. So we know that humans face many self-control problems in areas such as not saving enough for retirement by spending too much in the present, or procrastinating instead of doing things like exercise or studying that we should be doing. And commitment devices have often been proposed as solutions to these problems. The reasoning being that it can help the present biased agent to avoid choice reversal, or even if the agent does not succumb to temptation, it can also avoid costly self-control. And there are plenty of examples of commitment use in various settings in the literature, such as grocery shopping, gym attendance, and of course work tasks in the lab, including Severine's paper from 2018. But what is notable in the literature so far is this lack of overlap between the need and the demand for commitment, which can of course give rise to under or over commitment. And so far the focus has been on under commitment. So for example, naive or partially naive agents not buying enough commitment, or at least a sufficient level to completely eliminate the failure in self-control. However, recent research has also indicated that commitment demand is present even amongst those who don't seem to need it. So in Rohr et al., people have commitment demand even if they have been exercising regularly anyway. And in Toussaert et al., we find that commitment demand is concentrated amongst those who are dynamically consistent. So these people don't actually suffer from choice reversal. So it seems that overcommitment might be a problem, just like undercommitment is. But so far, the welfare implication is unclear. So there hasn't really been any study that looks at whether or not commitment demand leads to a loss in expected utility. So this is where we hope that our study would contribute. So we are going to quantify the different components of facing temptation, be that material loss or psychological cost, and we're going to compare these with subjects' stated willingness to pay for a commitment device that removes the temptation. And by doing so, we're going to be able to see whether or not there is overcommitment, how it compares with undercommitment. And in the paper, which we won't have time to go through today, we also study what motivates it. And we do this in a lab experiment with the following setup. So first, subjects are going to complete an attention task without temptation. And this is done to measure their productivity. And this task is very similar to the one used by Toussaert 2018. So for a period of 30 minutes, subjects are asked to pay attention to the screen, where a 4-digit number updates every 3rd second. At 5 random times, they're asked to enter the last digit that they saw, which of course they can only do correctly if they have been paying attention in this boring task. And if they do answer correctly, they can earn about €5. So in total, for 30 minutes, they could earn €25. This is quite a lot of money, intentionally so to motivate them to pay attention. At the end of these 30 minutes, they also get feedback about how many of the 5 questions they answered correctly. And then following that first task, we elicit the willingness to pay for a commitment device. Basically, we tell subjects that you're going to be repeating the same task again, but the second time, there will be an option to access the internet. And they are shown how this screen will look like in their paper instructions. They get a screenshot. And we tell them that if you click this internet access button, which presumably is tempting because the task was boring, it will stop them from earning more money from the attention task. But if they would like to remove this internet access button, for example, if they think they might be able to concentrate better without it, they can do so, and we explain to them basically the BDM mechanism. And this is implemented with 50% probability in order for us to observe as many subjects as possible facing temptation even after demanding commitment. After that, we elicit some beliefs. So we ask subjects what they predict they would get out of 5 in the second task. Firstly, if they do not face temptation. So Y NT for no temptation. And then what is their predicted score if they face temptation, YT, if they succumb and click the internet button, if they don't succumb, and finally, what is their predicted likelihood of succumbing. And we put hats on all of these variables to denote that these are the subject's estimates. And then we also ask them whether or not they would like to revise their willingness to pay that they stated earlier. And we explain to them that the second willingness to pay is the one that's going to count. This is also the value that we are going to use in the rest of our analysis. And the reason for eliciting this twice is just to allow subjects the opportunity during this belief elicitation period to reflect upon how their productivity would be affected under temptation, and basically to reduce the measurement error in willingness to pay elicitation. Following that, they then go on to the second attention task, either with temptation or without, depending on the outcome of the BDM mechanism. In our analysis, we also use other variables, so let me just quickly introduce them. Of course, we have subjects' actual realized outcomes, so Y1 and Y2, their productivity in task 1 and task 2. And then we also elicit their actual temptation strength. And this is basically a question at the end of the experiment where we ask them, so was ignoring temptation easier, harder, or neither easier nor harder than expected? And we set this variable V equal to 1 for the subjects of interest. So these are the subjects saying ignoring temptation was easier than expected, since they are possibly or potentially the ones who might be overstating their commitment demand. And then we also elicit other demographic variables, including the brief self-control scale by Tang et al. So the sessions were conducted at Masaryk University in the Czech Republic last year with 289 subjects. And out of task 1 and task 2, we choose one at random to pay. So average earnings were about 28 euros. And the experiment was pre-registered on Open Science Framework. And recently, we've also uploaded the results according to the original analysis plan. So it's available up there. So before proceeding, let me just outline our strategy for how we're going to conduct the analysis. So first, we're going to state subjects' expected utility for stating a specific willingness to pay. We're going to optimize this expected utility function to yield the optimal or the rational willingness to pay as a function of realized material loss and psychological costs. And then we're going to compare these realized outcomes with subjects' stated willingness to pay to say whether or not willingness to pay is too high or too low. All right, so what is the expected utility function? We assume this function consists of the material wealth less any psychological costs from facing temptation. And the first two lines refer to the case where task 1 is paid, which happens with probability of a half. And the last two lines refer to the case when task 2 is paid. So let me just go through when task 2 is paid. So the third line refers to the case when the BDM is not taken into account, which happens with probability of a half. So here subjects have to face temptation regardless of their willingness to pay. And their utility then consists of 100 participation fee plus 120. So this is 120 Czech crowns that they get per question, or €5 per question, times the number of questions they got correct in the second task with temptation, hence the superscript T. And then minus the psychological costs from temptation. In the fourth line, Here we have basically the case when the BDM is taken into account, which again happens with probability of a half. Then with this probability, 100 minus willingness to pay over 100, their willingness to pay is not sufficiently high. So it's lower than the random number that we draw in the BDM. And so they still face temptation, again with the same utility. But if their willingness to pay is higher than the random number that we draw, then they successfully bought the commitment device. And their expected utility is given by this integral of 100 participation fee plus 120 Czech crowns times the number of questions they got correct with no temptation, since they successfully bought commitment, less R. So R is the random number drawn that they will have to pay to buy the commitment. So this very complicated utility function, when we optimize it, gives a very simple expression for willingness to pay. So then the optimal or the rational willingness to pay for a commitment is simply the sum of expected material loss and psychological costs. So now that we know what willingness to pay should be or should rationally be as a function of material loss and psychological costs, we are going to compare for each subject their realized outcomes, so their realized material loss and then subsequently psychological cost, with their stated willingness to pay to see if it is overstated. First, we begin by assuming that subjects don't care about psychological costs, so that willingness to pay only consists of actual material loss. So we're going to compare their stated willingness to pay with 60 times y1 minus y2. If it is overstated, then we know that subjects are either incorrect in their expectation of material loss, or that they do anticipate some psychological costs from temptation. To eliminate that first possibility, we then compare willingness to pay with expected material loss. So y hat mt minus y hat t. And if this is still overstated, then we know that this is because of subjects anticipating psychological costs. And finally, we're going to compare willingness to pay with actual material loss and psychological costs. And if this is still overstated, this is where we say there is overcommitment, that subjects are incorrect in their expectation of material loss and or psychological costs. So here are some summary statistics from the experiment. Out of 289 subjects, 27% of them have positive commitment demand. And out of those 27%, the average value they're willing to pay is 26 Czech crowns, or about €1. So this is similar to previous studies finding quite low demand. Out of those 289 subjects, because of our random implementation of the BDM, the vast majority, so 277, still face temptation, with only 4 succumbing. So our analysis is going to focus on these 277 subjects. So those subjects that face temptation can be categorized into 3 categories based on their material loss. So first we have the ML, or material loss overestimators. So these are the subjects stating willingness to pay greater than 60 times y1 minus y2. So as you can see here, under the column y1 minus y2, these subjects actually do better under temptation. y2 is greater than y1, and they should have stated a negative willingness to pay, or at least 0, since 0 is the minimum that we allowed. But in fact, they stated a willingness to pay of 19. So they are overestimators, and they make up 22% of our subjects. At the bottom, we have the underestimators. So these subjects actually do worse under temptation by about 1.5 questions. And according to our optimal willingness to pay, they should have stated a willingness to pay of 60 times 1.5, so 90. But they only stated 8 on average. So underestimators, these people make up about 6%. And the rest are what we call accurate estimators, and they make up about 3/4. So then we can go on to the first point under our earlier strategy, where we compare subject stated willingness to pay with the actual material loss. And here we hypothesized that overestimators make up no more than 10%. And why 10%? So this is an arbitrary threshold, since we didn't really have any existing estimate for how much confusion or any demand effects would affect subjects in this setting. But we argue that this threshold is actually conservative because by this point of the experiment, they would be familiar with the attention task and also with internet just as a temptation. So there should be very little confusion, and also a recent paper by Duquette et al. Bounding demand effects. When we use their estimate in our setting, demand effects should not be more than 6% of our subjects. So then when we do the hypothesis test, we find that, as I earlier stated, 22% of subjects are overestimators with respect to actual material loss. And this is significantly higher than the 10% threshold, and also compared to the 6% underestimators. So it seems that overcommitment in this setting is more widespread than undercommitment. However, when we calculate the welfare loss from the overestimators, this is less than half that from underestimators. So in some way, this vindicates the existing literature's focus on undercommitment as a problem. So next we compare stated willingness to pay with subjects' expected material loss to see if it's more accurate than their actual material loss. And here we find that still 18% of subjects are overestimators, meaning that it's not because subjects are wrong in their expectation of material loss, but rather because they do anticipate the psychological cost of temptation. So 18%, this is slightly more, but not significantly higher than the proportion of underestimators at 15%. And finally, we incorporate psychological cost to see if willingness to pay is still overestimated. And here, of course, we can't measure psychological cost directly. So what we're going to do is the following. We're going to say that there is overcommitment if the willingness to pay stated by the subject, which should be based on their expectation of material loss and psychological cost, if that is greater than the rational or the optimal willingness to pay, which should be based on actual or realized values. So this is why we have the inequality on the left-hand side here. And then it's just easy to plug in the components of willingness to pay, so 60 times YNT minus YT and plus PC. And here we denote with the subscript E on the left-hand side all variables that are expected. And with A's on the right-hand side, variables that refer to actual or realized values. So then we just bring in all the material loss variables to the left and PCs or psychological cost to the right, and we end up with the inequality on the second line. So what this says is that a sufficient condition for overcommitment is that the left-hand side is greater than or equal to 0 and the right-hand side is strictly negative, or the left-hand side is strictly positive and the right-hand side is less than or equal to 0. The left-hand side is just the material loss variables, and these are very easy to plug in using what we had before, y hat and t, y hat t, y1 and y2. But for the right-hand side, since we don't have a measure of psychological cost, this is where we use the v variable I talked about earlier. Since we want the right-hand side to be strictly negative, for the left-hand side to be greater than or equal to 0, a negative right-hand side means that PCE has to be greater than PCA, meaning that subjects should experience the temptation to be easier than expected to ignore. So these are the V equals 1 subjects that we were interested in. So then we can identify overcommitment according to this definition stated in hypothesis 3. And of course, necessarily willingness to pay has to be greater than 0. According to this criterion, then we have 15% of subjects over committing, and this is significantly greater than the 10% threshold, and also than the underestimators, which by this definition only makes up 7%. So unfortunately, we can't measure psychological cost, meaning that we can't calculate the welfare loss. But of course, if we include psychological costs in the rational willingness to pay, that value should be higher, meaning that the overall welfare loss from overestimators would be lower, and the overall welfare loss from underestimators would be higher compared to those values that we found under hypothesis 1. So yeah, those values, those comparisons we made earlier would be even greater. So we don't have time to talk about the drivers, but it will be in the paper if you are interested. So let me just conclude by saying that we conduct a lab experiment, finding that there is excess demand for commitment, not only compared to material loss, but even when we take into account psychological costs. which so far has eluded field experiments for obvious reasons. We find that overcommitment is a more widespread phenomenon than undercommitment, although the welfare loss is larger for the latter group in the setting. And in the paper, we also show that overcommitment seems to be driven by self-control. So taken together, our results point to the need to consider heterogeneity in subjects' preferences, and in particular, the fact that commitment demand can be harmful to some subjects, and therefore, more commitment is not always better, and perhaps there needs to be an upper limit in commitment. So that's it. Thank you very much.
Thank you very much, Margaret. Now we'll have Severine Toussaert from Oxford, who will discuss this paper. You are muted, Severine.
Thanks. So can you guys see my screen?
We saw your screen for a little bit, but now it's gone.
Oh.
Can you reshare it?
Yep. Okay. Good?
Yes, perfect.
Awesome. So thanks a lot, Margaret, for a very nice presentation, and thanks for having me as a discussant. Always a pleasure. So really nice paper. I think it's clear, it's careful, it's very polished, very nice read. Enjoyed going over it. The paper really takes an unusual take on this literature, looking at commitment demand, usually focusing on the idea that people are naive about their self-controllability and therefore don't commit enough. And you're taking the opposite stance that maybe people might actually be pessimistic and therefore overcommit. And so what I like about that is I think there's not a lot of work, in fact, looking at pessimism and underconfidence. I mean, you're massive literature on over-optimism, overconfidence, but still a topic that's not explored as much. I mean, and this asymmetry is quite interesting to me. So I like the fact that there's this emphasis on that front. Speaking about overcommitment, I mean, you speak more broadly about, the paper speaks more to this literature suggesting that commitment may hurt, right? So maybe people might be better off without the presence of, external commitment contracts. And so you cited a few papers going in that direction. It also speaks to a theoretical literature. I'm thinking about, for instance, Benabou and Tyrrell have a paper on intrapersonal rules, suggesting that people might, sometimes adopt overly rigid rules because of their, imperfect knowledge of their self-control. So I think it nicely fits in this literature and takes an interesting stance. What I also really like about this paper is the serious effort you've made to try to decompose the willingness to pay for commitment. So you're really trying to measure, the expected productivity loss from being exposed to temptation. It's not something I had done actually in my paper. In some exploratory analysis, I'd exposed that there were differences in productivity for subjects who were exposed to temptations versus not, but I don't know if it was anticipated by subjects. So I really like this effort. You also try to obtain, finer measures of beliefs about, the chances that people face of succumbing to temptation. You do that from different, using different methods. So I find this is very useful, and you try to complement this with some, subjective measure of the psychological cause of temptation. Admittedly a bit noisy, but we can go back to this. Usual rant on this literature is I so wish there was actually a paper meta study looking at commitment take-up and really trying to understand what are the determinants of commitment demand. But here, within the context of your paper, really trying to decompose this, I thought was very good. Let me try to challenge you on two things. Okay. So the first thing is about the importance of the question. Okay. So the first time you spoke to me about this question, I was wondering, why should we care about this question, right? And one of the points is, we're talking about a subset of people. There are few people who commit. We're talking about a quarter. And then within that quarter of people, then you're thinking about, the people who overcommit, right? So at the end of the day, we're talking about small numbers. And so that might make the question less interesting from that point of view. We're talking about something that's not very prevalent. On the other hand, I think it's an interesting, important question from the perspective of welfare aggregation. So you already mentioned the issue of heterogeneity. I think that studying this is very important if the harm that's due to overcommitment actually exceeds the harm due to undercommitment. And one of the reasons why I think this might be possible is that if you think about commitment, well, it completely shuts down the channel of learning. If you're trying to learn about yourself, you actually remove yourself from certain environments where you might be learning about, for instance, your self-control ability, and it might actually have serious warfare consequences, especially dynamically. So I think this is something potentially you might want to emphasize more in your work. Let me go to the issue of welfare. Okay, so the measurement of welfare. I do want to say something about, overcommitment, right? And so here, well, this is a difficult exercise because we really want to try to understand what's in the decision maker's utility function. And so you really have a good grasp of like the material consequences and the perceived cost from this, productivity losses. There's the issue obviously of non-material costs. So thinking about self-control costs, that's super hard to measure. And then you mentioned this a bit also in your paper, and there's an issue that there are many other things that could be entering in the decision maker's utility function, including self and social image. So maybe there's low chance I succumb to temptation, but then the cost to me of having succumbed is very high. I also like to argue that maybe commitment has also some signaling benefits. So if commitment is actually hard, if only the naive guys don't take the commitment device, maybe actually I might signal my determination, my motivation to do a task by committing. And in fact, that would actually generate benefits and justify commitment in the first place. And finally, I'd like to go back to the measurement of beliefs. Okay, so I find this idea that people are pessimistic, they kind of anticipate they're going to do worse, very interesting and puzzling. And in fact, in my paper, there was also this issue of people, overestimate their chances of taking the sort of tempting option. And so, yeah, I would like to ask, what if it came from motivated beliefs? I might have an interest in convincing myself that the task is going to be tedious, so I remain attentive, for instance. And I think we need to try to understand a bit better, where does pessimism come from, and relate this to the issue of motivated beliefs. So I really like your effort on measurement, and I think we need to dig in further and really try to understand what is in the decision maker's objective function. Thanks a lot for your talk.
Thank you, Severine. Margaret, would you like to take a minute to respond?
Yeah, thanks a lot, Seth, for discussing this and of course giving all the previous comments you've given on this paper in the past. So definitely plenty of things for me in class to talk about and potentially improve the paper with. So just relating to the self-image point, I find it's really interesting as well, right? Because so you mentioned that if people derive self-image from committing being a good signal of sophistication, then commitment potentially also has positive welfare effects. But one thing that we have been perhaps trying to get at is if it's possible to see if facing temptation and then succeeding actually gives some welfare benefits that people might miss out on by committing. And this is related to your point about learning as well. So yeah, not directly addressing the question perhaps, but yeah, definitely something interesting to take in the future. So thanks again.
Perfect. We have one question in the Q&A and we have a couple minutes left. The question is directed to both Margaret and Severine, I believe. Which tests of optimism and pessimism would you recommend? Do either of you would like to respond? Maybe Margaret, do you have an answer in mind? If not, maybe Severine.
So I can say about how we measure pessimism. So here, obviously we have beliefs elicited from subjects about how well they predict they would do under temptation, and then we have the realized outcomes. And so we say that subjects are pessimistic in that sense if their expected material loss turns out to be lower. And with regards to the V variable we talked about as well, so if V equals to 1, then subjects are pessimistic in the sense that exposed the temptation was actually easier than expected. So this is how we define it.
Okay, we have a minute left. Are there any other questions from the audience? Feel free to raise your hand. If not, we can come back to the questions at the end during after party as well. I'll have Ian now introduce our second speaker. Thank you both.
Thank you so much. So I have the pleasure to announce our second speaker for today, who is Erhao Xie. He's currently at the Bank of Canada and received his PhD from the University of Toronto in 2018. Today he'll be presenting his work in progress, monetary payoff and utility function in adaptive learning models. So Erhao, whenever you're ready.
Thank you. Let me share my screen. So thank you so much for having me, and thanks you for your attention on this paper. So since I'm from Bank of Canada, I have to first say that the views in this paper is my own view, and it doesn't represent the views from Bank of Canada. So this paper lies in the context of learning in games. So commonly, when we have the case that players face a new game for the first time, so it is difficult for them to choose the equilibrium strategy, and there are several reasons. For instance, bounded rationality or like multiple equilibria. And on the other hand, if players can play identical or similar games for many times, they can potentially learn from their experience, and this learning process could change their choices across time. So in the game theory, the learning will relate to at least 3 core questions. So first, will players' behaviors converge to an equilibrium? And which equilibrium will be reached if multiple equilibria exist? And what is the speed of the convergence? So due to this importance, and you can imagine there is a large literature to study players' behaviors, players' learning behaviors. And in this paper, I shall focus on a general class of adaptive learning models. And in particularly, I will study their empirical properties and identification results. So next, to fix idea and emphasize why you may care about these results, so let me start with a very simple matching pennies game. So in this game, if 2 players' actions match each other, then player 1 will get a utility or payoff equal to 1, and the player 2 will get nothing. And their payoff profile will switch if their actions don't match to each other. So this is a standard matching pennies game. So now let me do a very simple transformation of this game. So I just add 2 to every payoff profile of this game. So from the micro theory, we know that this kind of affine transformation will preserve the same preference. So from the game theoretical point of view, these 2 games are actually identical. They have the same best response functions and the same Nash equilibrium. However, what's the interesting thing is that if we consider many existing learning models, and these learning models would imply that these 2 identical games will have very different learning paths. So in this graph, I just simulated the choice probability of X for player 1. And this is a simulation projected by the experience weighted attraction, or EWA for short, model. So this model has been proposed by Camerer and Hu in 1999 and has been the benchmark model in this literature. So you can see there are very different learning paths. So players learn very quickly in game 1, and their the outcome converge in around the period 40. And the learning process is very slow in game 2, and it seems that the players are still learning at the final period. And even though these 2 games may converge to the same outcome, which is the unique mixed strategy Nash equilibrium, they have very different learning paths. And I would like to say that this result holds true not only in this particular game, but any other types of games. And especially in games with multiple equilibria, you may even have these two identical games converge to very different outcomes. So this is actually my first key result of this paper. So I show that adding a constant to the utility or payoff function can change players' learning paths in a set of learning models. So the result holds true not only in the EWA model, but also other learning models such as payoff assessment learning and impulse matching learning. So I was very surprised when I first derived this result. So it seems that this property contradicts with the standard decision choice theory. However, on the other hand, all these learning models are well-founded and they are shown to fit or explain players' behavior quite well. So I would like to try to understand this property in the context of this learning model. So the argument I want to push in this paper is that the utility could have a distinct interpretation in this context of learning. While this may sound crazy at the first glance, but if I look at the model in detail, I think it actually makes some sense. So what I mean is that the utility, the way that the utility enters into this learning models means that this utility does not necessarily represent players' cardinal preferences that measure players' welfare. Rather, this utility measures players' subjective evaluation about the successfulness of each outcome. So even though preference and successfulness may be correlated, they are very distinct concepts. And I will discuss more later. And regardless of whether you buy my argument here, the above empirical property has another implication on the estimation of learning model using experimental data. So in the experiment, we normally give subjects money to reward their performance in the game. And normally we would assume those monies are just players' utilities. So that is UM equal to M. Of course, this restricts to risk neutral and no social preference. However, my above property shows that there is a fundamental problem in the estimation of learning model. This is because even though players are risk neutral, but assuming UM equal to M and UM equal to M plus some non-zero constant C would have very different implications or predictions. And ex ante, we don't know which specification is correct. And the potential misspecification of this utility could generate considerable bias on both learning parameters and counterfactual predictions. So to solve this econometric issue, I propose to specify utility as an unknown non-parametric function of money. And then we estimate utility together with the learning parameters instead of assuming utility is money. And then I can show the identification of both terms under quite weak conditions. So regardless of the first main result, I think this identification result has its own interest. So when you don't want to impose any functional form restriction on the utility, you can apply this identification result to also estimate the utility function in the learning model. With this two results in hand, I perform an empirical exercise with a large-scale experiment, which was conducted by Zelton and Chmura in 2008. So I found the utility function in earning is concave in the monetary payoff. And moreover, UM or utility of $0 is not zero. I think this is a fairly important result, and I will discuss more about its interpretation. And assuming UM equal to M will generate a considerable bias on the learning parameters. So to discuss further about all these results, I consider in the framework of EWA, though the results holds more general. So we can consider a very simple normal form games with n player, and the player is indexed by I. So, and the player's action are indexed by J and denoted by the small s. So the payoff function is denoted by pi. So this normal form game is played for t periods, and SIT just represents I's actual choice in period t. So in this EWA model, the model tracks two evolving variables. So the first variable is the experience NT. So it can be interpreted as the observational equivalent number of games that player I has been played up to period T. And it evolves like this. So here rho is just a forgetting parameter, measures people may forget their own experience. The model also defines attractions for each action at each period. And these attractions determine each action's choice probability. So specifically for action J, its future attraction is a weighted average or weighted sum of its current attraction plus its current payoff if this action J has been chosen at the period T. So you can imagine if players has more experience, the current payoff has a less weight. On the other hand, if the action J is not chosen at the period T, then this action J's payoff is actually a foregone payoff. And to measure, people may pay less attention to their unchosen actions. Then the EWA model has a discount factor delta here to measure about this, like maybe non-cariness of foregone payoff. And as the author argues, this delta is one of the key innovations of the EWA model. As we vary this delta, the model can capture two mainstream learning models, which is belief-based learning and reinforcement learning. So given the attraction, one player can be seen to maximize a perturbed attraction. So here, epsilon is just a random perturbation to player's attraction. It can be also interpreted as the decision error or calculation error. And here, lambda is just the sensitivity parameter, measures the scale of the epsilon. So my results holds true for any distributional assumption on the epsilon. And a common assumption in the literature is this epsilon follows IID Gumbel distribution. So the choice probability of action J follows the standard logic formula. So this decision framework is essentially the discrete choice decision model pioneered by McFadden. And from that literature, we know that there is a one-to-one mapping between players' choice probability and the difference of attraction. So we only need to calculate the difference of attraction to get the choice probability. And here I'm doing this. So what I'm going to show is the property that add a constant to the utility function. So if we just plug the evolution equation for A, then we could get this expression. It's not that important for now, but consider that we just add a constant C to the payoff function pi. Then this term is essentially fixed. This term increased by C, this term increased by delta C. So these two terms essentially cannot cancel out. So the relative attraction of action J is actually increased by this amount of thing. So if delta is not equal to 1, then this term is non-zero. So the future attraction change and the future choice probability change. So this is actually one of my key results. So the choice probability for any time is invariant to adding a non-zero constant C to the utility function if and only if delta equal to 1. So we may wonder what's special for delta equal to 1. So as Camerer and Hu showed, so when delta equal to 1 with some transformation, we can interpret the attraction or A as an expected utility. So in this way, we have this result as the standard decision model. So adding a constant to the payoff function doesn't change the choice probability. However, when delta is smaller than 1, we don't have that expected utility interpretation for the A. Therefore, adding a constant will change the choice probability. And when delta is not equal to 1, this captures the idea that players may evaluate chosen and unchosen actions very differently. So this feature is, I think, is well founded in the psychological literature and is shown to fit the data well. So I'm not going to change that thing, but instead interpret this utility property in context of this learning model. So to facilitate my interpretation, we can consider a very simple cumulative reinforcement learning model without discounting. This is also a special case of the EWA model with this parameter value. So the future attraction is its current attraction plus pi if this action is chosen. And if this action is not chosen, then player I will not receive any information on the payoff of action J. So her future attraction is fixed. So it's the current attraction. So this model actually captures the idea that individuals tend to choose historically successful strategy, because you can imagine when this pi I is larger, then future AJ is larger, and the player is more likely to choose J in the future. So if we buy this interpretation, then this pi I actually measures the successfulness of action J rather than the preference for action J. So even though they are may related, but they are distinct, and I want to say their difference using this very simple example. So imagine we have a simple environment where player can earn from $0 to $100, and consider a simple strategy that increases my monetary reward from $0 to $1. So if I'm risk averse, then my marginal utility is very high. So this strategy may substantially increase my utility. However, since I don't get many other higher payoffs, I may not really consider this strategy as successful. So I may not choose this strategy in the future. So this could explain the difference between successfulness and the preference. And based on this interpretation, we can also interpret the constant add to the utility function. It exactly measures the successfulness of $0. So for instance, if we consider a zero-sum game, and if I'm loss averse, then I may view a strategy with $0 as pretty good. However, if we consider another context of coordination game, I may, all the players could earn positive money. Then I may view a strategy with $0 as unsuccessful. So this gives us an interpretation of utility of $0 in this learning context. So, and this is pretty much what I want to talk about model part. And the final thing are just some econometric issue. So as I discussed, this pi I intrinsically is an unknown object. And if you believe my argument, then this pi I is successfulness, not necessarily preference. So we cannot get pi I from any preference elicitation method. So what I propose is to specify pi I as a function of monetary payoff. And then this U is just a non-parametric utility function. So with this specification, we have three sets of identification objectives. So learning parameters, utility function, and the initial state variables. So my second result shows that under weak condition, all these parameters are identified. And we can consider two different asymptotic here, either number of subjects approach to infinity or number of period approach to infinity. So since I'm maybe out of time, let me just quick summarize my empirical finding. So I estimate with an existing experiment by Zelda and Chmura. So we have 12 different matching pennies game. And this is one example of this game. And the number here represents the monetary payoff. So we have almost 900 subjects played 200 periods, and each period is randomly matched. So what I want to first say is that when we incorrectly impose the monetary payoff as the actual utility, we can substantially underestimate parameter delta, which by 50%. So this is a huge bias. And also the utility function here is concave, represented by this blue line. And you can see we can reject this black line, which represents the assumption that the utility is money. So moreover, the utility of $0 is negative. So this is very plausible given my explanation, because players participate into experiments to earn money. And if they may earn $0 in the game, then they may really view this as an unsuccessful attempt. So I think this is all my estimation results, and I may stop here. Thank you.
Okay, thank you so much, Erhao. We now turn to Colin Camerer for discussion. Colin?
Yeah. Sunrise behind me because I'm in California. Thanks for putting this together. I don't have any slides, so I'm just going to say a few words and try to fill in a little bit of what Erhao has done. So this is a great paper. It's very, as somebody who worked on this general topic in the late 90s and 2000s when lots of people were throwing ideas in, it's really nice to see people continuing to innovate on what are really fundamental questions. You know, often in the literature, the first wave is, you know, there's a to-do list and you're interested in, say, comparing fictitious play with reinforcement, which is fundamental in first order. But there's a lot of other subtle important questions. One that Erhao talked about obviously was what exactly is being reinforced, or what are the utilities? And this, besides social preferences, we may not think it's just pure money. There could be risk aversion in the utility function. And we and most people like to just put that aside. It's like, unless we think risk aversion is going to somehow then also interact with learning, we're going to assume risk neutrality, even though we don't believe risk neutrality for the usual reasons in all areas of economics, you know. However, I should add, there's a recent paper by Annie Liang and Drew Fudenberg that shows that if you include risk aversion of a very simple power utility, that explains some game theoretic predictions better, which again, it shouldn't be really surprising. And the picture Erhao showed of the derived utility function, which seems to fit the data, in this case, learning data, like a learning path, shows pretty much the same effect. If you put in some risk aversion, that's going to do better. And it will improve identification of the learning parameters. So it's just a specification. I think the whole point of this is that being careful and adding things and thinking very carefully is almost always going to teach you something either kind of important or maybe very important. Second thing is in around the 2000s up to 2010, there were some papers like by Tim Salmon and Nate Wilcox and others, which and Erhao's paper is extremely careful. He covers all the old literature, and then it's super methodical, like for someone like me anyway, crystal clear. There was a lot of pessimism, I think, of identification, and I don't worry about identification. I'm not sure junior people should be like take my advice on this, but often the concern about identification in classic econometrics is sort of like the worst case scenario. Similar to in computer science, they're often worried about the worst case performance of a heuristic. But we have a lot of checks in experimental economics. We have a lot of checks against identification problems. We can do out of sample testing, right? If you really haven't identified parameters, there'll be a big degradation from in-sample fit to out of sample. We can run more experiments. We can do Monte Carlo. And Erhao did most of this, right? He did Monte Carlo to look and see what the, if you fix free parameters, what's called ground truth recovery, and then you use a procedure, do you get the truth or not? It turns out like, no. If you assume U of M equals M and you're wrong, you get the wrong number, which he showed us one graph like that. So you can always do more, you can always do more. And this is related to a very modern, I think, contribution. This is something we could not have done 20 years ago, which is kind of designing for identification. So one reason the results are so beautiful and pretty clear is Erhao's using this data set of 200 plays of games. So you get a long learning trajectory with 864 people. So you have a lot of people and power, and you can even then potentially start to look at heterogeneity and clustering, are there different types and things like that. So nowadays, part of it is thanks to COVID-19, prolific and MTurk and budgets and the fact that experimental economics is booming in a lot of different places. Instead of saying, is this model well identified under typical experimental conditions of like 100 subjects playing 20 times, that's like, who cares? The question is there a feasible data set? How many periods of learning would you want to see, and how many subjects would you want to see, so that we could then identify and learn a lot of stuff? And I'll say one last thing, which is there's a sporadic but very deep connection between this class of models, that is these models with delta and then foregone payoff and chosen payoff, and neuroscience. So as we were working on this in the 2000s, it sort of emerged that one of the key ideas in theoretical neuroscience, which is very useful, I think, for economics, is that there's sort of two learning systems operating in parallel. One is called model free, which is basically an old reinforcement, like I did something, it worked, I do it again. I bid in the auction and I won money, I do it again. Or I lost money in order's curse, I quit bidding. And the other is called model-based, which is how we almost always think about game theory. So model just means you have a mental representation of what all strategies will yield in terms of outcomes, and then either rewards, payoffs, or as Erhao says, like a success rating, like a psychological reinforcement level. And so once you think about these papers like EWA and others as essentially like mixtures of different model-free processes, like the Severine and Vahid papers on general assessment learning, and the newer paper, the driver is just reinforcement. It's model-free. It's like, I did it, worked, do it again. I did it, and that's a good model of non-human behavior. It may, because non-humans are less likely to build a kind of world model unless it's something that's genetically installed or that they're very equipped to build, like in spatial navigation and foraging for animals looking for food. Anyway, so I think one frontier, I don't think many people here are interested in this, but they're just kind of alerting you that other people are, like Ming Su and Lu Xiaozhu, who is my student and kind of grad student. They have some papers looking at neural circuitry. And once you think about this model-free, model-based distinction is analogous to delta equals 0 and delta is positive, you can start to open up all kinds of possibilities. And the last thing is, which Erhao didn't have time to go into, was he finds some really interesting results where, suppose you allow the weight on something that didn't happen, but you can imagine having happened because you're using your model-based representation, right? Which is the foregone utility. And you could divide that into things that would have been worse and that would have been better. And you could think how, like, from a learning point of view, you might overly focus on what would have been better in order to learn. or what would have been worse. And it could be that garden variety pessimism, you know, about, am I the kind of person who dwells on how much more I could have had, or I'm the kind of person who says, there for the grace of God when you know, at least this bad thing didn't happen to me. So there's some scope in those parameters. And in the estimation results, he gets very large deltas of those type greater than 1, which is certainly plausible. I mean, I would have thought mostly what people actually receive or animals actually get, like food, compared to they look at their neighbor and their neighbor gets more food. There's a natural like privilege of what you get versus what you observe or what you see or what you counterfactually imagine. But that need not be true. And if the numbers tell us that something else is going on, that's very, very interesting and extremely novel and probably well identified because of all the care in this paper. I should add one more thing, which is I first talked to Erhao about this a couple of years ago. If you're working in a serious job where you have to get up early, like at 7 a.m. Every day, like at Bank of Canada, to be able to produce a paper like this is really extra difficult because it's completely up to date. It's crystal clear. I hope you can publish it well. And it's hard enough to publish papers in any circumstance, but when that's not your 100% full-time job, that's terrific. So I'm glad to see that this paper looks finished to me and it has a lot of cool stuff in it. Thanks.
Thank you.
Wonderful. So I think that we are just about out of time and ready to move into the after party. Let's see here. So Yan, would you like to?
Yeah. So if you didn't get to ask questions, feel free to ask them during the after party. You can raise your hand and we'll promote you to become a panelist so we can start a discussion. So if you click the participant button, you should be able to see the raising hand function. Okay. So if there's no question from the audience, I'm going to take advantage of my position and ask one for Erhao, which is about the sort of the psychological effect of adding this constant. And what you did was to treat it as a you model risk aversion. Alternatively, one could think of, you know, if someone has a target income, you know, instead of adding $2 to each payoff, I can add $1 million, right? And if I add $1 million, the difference would be between, you know, I get $1 million and my opponent gets $1 million and $1, and then it will probably never converge. So the issue is it you know, reference point effect that I come into the lab, I have a target earnings rate, and therefore if I'm, you know, so I'm thinking about normalization. So have you thought of?
Right. So this is actually the key thing I want to emphasize in this kind of learning models, and also related to Colin's comment. So here, of course, the risk aversion or reference point matters here. But what I show, so let me share a little bit about my slides again. So here, the difference of this graph is really not about the risk aversion. So here you can imagine what I put here is not just the monetary payoff, but the actual utility. So you can think is, so in the paper, I have another game where you have the monetary payoff and you have the actual utility, I assume to be square root of monetary payoff to capture the risk averse. And then I have another utility function, which is square root of m plus 2. So here is the 2 I'm pointing about. this 2 is not necessarily $2, but it's a 2 add to this pi function, which is already we interpreted as utility.
So this is, the numbers are, I'm sorry. So I want to clarify this. So the numbers, your interpretation of the number is it's already U of M.
Yeah, it's already after taking the risk aversion. And
Okay.
I mean, after you taking account of risk aversion, then that constant still play a role. And I want to emphasize the role of that constant. So this is like further for simplicity, I just assume it's risk neutral, but I don't, but it won't affect my argument about this constant C. So the point here is that in the standard decision choice, we can also always do normalization, say utility of $0 to normalize to 0. However, in the learning model, in this learning models, we cannot do that normalization. It's actually an assumption.
Okay.
Yeah. So this is the point I want to convey.
Yeah, thanks. Okay, any questions from the audience?
I have a question. Yeah, I'm following a little bit on just what Erhao said. You can hear me, right?
Yeah.
So on the one hand, you might think, look, if you add a constant to everything in a game matrix, and that makes a difference, that's a big problem. But I think it's sort of the way around. In classic equilibrium analysis, if you add a constant, except for mixture probabilities and risk aversion, if you add a constant, it shouldn't make any difference. And in learning models like fictitious play, as Erhao carefully pointed out, in the McFadden type models, it's the difference in valuations that matters. So if you add a constant to both things, it subtracts out. But that's not really a virtue of those models. That's the model hiding from a complicated world. You know, in other words, it's a simplification to be invariant to adding payoffs, which is almost surely, sometimes it's first order wrong, sometimes it's just an adequate simplification. And certainly we can do, you know, you can give your students homework problems that are a lot easier to solve. But once you include this sort of wedge between model-free learning, which puts kind of full weight on the received payoff or the success measure, let's call it, and then a different weight on unchosen payoffs, then adding that same constant is going to make a difference, because you're not adding this AI minus AJ is not fixed. It's AI plus some number minus AIJ plus delta some number. And if you think about the psychophysics of valuation and so on, you know, there's almost no way you should have invariance to payoff transformation if you're trying to describe what people are doing. And then the next question is just a messy one that Erhao has tackled in the right way, which is let's parametrically think of what may happen. Let's try to like do some fitting. Do these numbers make sense? And I think the general, if you're learning in the domain of gains in a game, the general effect of adding an affine transformation, just adding a constant to everything, is going to be to kind of retard the rate of learning, because you're always going to put a high weight on wherever you got and a less weight on something you didn't get. So you can think about, say, companies, you know, why are companies that are earning so much money, you know, so slow to adapt? And the answer is that the weight on unchosen payoffs from doing something different that might be better is low. And they're, you know, they have a high earnings. So it's going to look almost like a satisficing or getting stuck in like a good outcome. And it's going to be stronger the more they're kind of earning, right? So you can start to speculate about where you might see these things outside of just the, but the starting point should be exactly where we are, which is, let's kind of write down some equations, think about where the, what behavioral assumptions are actually very aggressive, and then start to kind of relax them and think of what that means and look at more data sets and so on.
Yeah, so let me just add another point. So I think, yeah, I think this is actually some good property of these learning models. Given Yan's example, so if you just add $1 million to the payoff metrics I I put there, then probably you would see every action is kind of successful action. So even though initially you choose maybe not optimal strategy, but you already choose the successful strategy. So that implies maybe this guy will stick into that strategy forever. So I think this could make sense in like normal day life decision. But instead, if this $1 million is deducted, then this guy may actively search for other better strategies.
Mm-hmm. Mm-hmm. Okay. Any other questions from the audience?
I have a question. It's Colin Camerer again for Margaret. I thought one of the takeaways from your paper, I mean, there are a number of obviously things that are interesting about it, was most people don't need commitment. They don't need commitment and they don't pay for it, 72%. And I thought that was really interesting. And I thought the discussion by you and Severine about, you know, why are people sort of overcommitting, and maybe they're kind of like self-virtue signaling or something. I mean, that's really cool and interesting. I think it's actually, I'm going to give you a kind of a tangent, which is some people occasionally and sometimes obsessively worry about ecological validity of are our experiments telling us something about certain kind of natural things that people do every day. And every day people do boring work and they have to like wait for a message to come in from the boss, or they have to be attentive to a string of numbers. It could be even something that seems fun, like foreign exchange, where you're looking at numbers on a screen, and you have to constantly know what the last number is. That's exactly what your subjects did, right? And they're tempted to do something that's more fun. So it may well be that task doesn't evoke, I should say, it evokes a type of temptation which is so lifelike, even though it's still very stylized. You know, nobody does exactly that job for a living and then has internet access and they can turn on internet access. But some people do things that are really close to that. And for that type of temptation, it seems like people have acquired a kind of personal rational expectations that they know whether they need the help of paying to turn off the internet or not. And most of them don't. And they don't naively forecast. They don't say, oh, I'm fine, I'm not going to get tempted by the internet. And then suddenly they're bored, like, oh, okay, nobody succumbs. I mean, that's amazing. You found like these superhuman people who don't succumb to the internet. I'm going to put my 14-year-old son, who's still sleeping, of course, through your test, and we'll see how robust it is. So I think there's a kind of glass half full property, which was a high degree of accuracy in self-forecasting in that particular task, even though it does seem to me like it would be very boring to do, and you might think, I don't need to pay for commitment, and then you turn out to succumb, but it just doesn't happen. I guess the question is how surprising is that? And to me, that's the most interesting finding.
Yeah, no, thanks for that, Colin. Yeah, interesting that you also think that this is perhaps not completely stylized in the lab, and nice to hear the example of the foreign exchange trader who has to do exactly this task.
Well, another, sorry to interrupt, another is like a security guard, right? Imagine these security guards that look at 10 screens, you know, probably there's a 1 in 8,000 chance, you know, other than some movie, that somebody creeps in and they're going to kind of like rob the bank. Mostly it's excruciatingly boring, and it's kind of painful because it's like, why am I wasting my time looking at this crap? Nothing's going to happen, you know. And of course, like in the movies, right, as soon as the guy, you know, checks his phone, all right, the burglary happens. So, so there, you know, there is often our designs. It's not that you tried very hard to mimic the bored security guard late at night, but it is actually pretty lifelike. And the fact that people are kind of pricing commitment mostly pretty well is really interesting. Although, you know, the opposite side is interesting too, that you and Severine thought hard about.
Yeah, let me just add something on this. I mean, I think that's one of the things that the reasons why I've been insisting. I mean, I really would like to see a meta study on commitment demand, because there is a lot of heterogeneity in terms of, like, you know, how much experience people are given with a task. So here, for instance, Margaret gives a lot of experience to subjects before the task. So totally, it's not a foreign task, but at the end of the day, you also, you know, you train your attention, you know, and so this might have a huge impact on your, you know, your commitment demand in the first place, and your ability to resist temptation afterwards. The second thing that I'm thinking about, which we haven't really measured, it is hard, is you know, sort of the potential substitution effects. I mean, yeah, there are many self-control strategies that could be using. One could be using an external commitment contract, you know, and they might feel actually pretty foreign to the decision maker on that front. I mean, thinking about some of the experiments where people make mistakes, I mean, this is kind of a potentially weird thing to be asked about. But every day we set ourselves goals, and they may actually be already commitments. And if people are very good at doing this, and you know, this could actually matter and explain some of the, you know, the reasons why people don't use this type of contracts that are actually costly for them.
Yeah, I have a question about this literature, which I'm not that familiar with, which is when you elicit people's beliefs, it always strikes me that why would we only elicit point estimates, which is, you know, how likely are you, for instance, to succumb to this unknown temptation in this unfamiliar task? You know, my naive intuition is that, you know, probably if you ask people, how confident are you about your estimate, you know, you would, if you allow them to give you an interval rather than a point, I think a better estimate is, you know, maybe the interval would decrease over time as they become more experienced. And there, if you elicit an interval, there's also a natural interpretation about pessimism versus optimism, which is you tend to use the lower bound of the interval or the upper bound. And so it seems that some of the standard tools in the ambiguity literature would be readily applied. I think would probably give us a lot of mileage over you know, the people's beliefs and then commitments.
Yeah, I mean, thanks, Jan. I'm actually working on a paper on this precisely.
Oh, okay.
So the point estimate is really something that actually bothers me quite a bit because I think just looking at differences in, you know, sort of this point, you know, belief that you gave and some outcome gives you very little, and in fact the distributions are, you know, highly skewed. So think about somebody who is asked, you know, how many tasks are you going to do? And the mode of his distribution is goal. Okay, that seems like a very reasonable thing. Yeah. But then put a lot of mass on, you know, not meeting his goal, which, you know, you understand that the goal is an upper bound, for instance. That actually really lead us to, you know, overestimate the extent of naivete of the decision maker by ignoring this, you know, the amount of uncertainty. I mean, the point you make about ambiguity, I think, is also very interesting and needs to be explored. But yeah, all this literature exactly looks at point beliefs, and it's not exactly always clear, not explicit what the moment of the distribution is that people are trying to recover from the experiments. Could be the mode, the average, and it's not necessarily the right statistics depending on the environment you're looking at. So I agree.
Yeah, so unfortunately, oh, sorry.
No, go ahead.
In terms of the probability measure, we didn't elicit distribution in that sense, and neither did we do this for the productivity measures. But what we did to try to address this is just seeing whether the results are robust to assuming that subjects misrepresent by, say, one question. So we tried using the same number +1 or -1, and we found that this is the results are robust to that. So yeah, but I agree, eliciting a distribution would probably have been the ideal thing to do.
Yeah.
Quickly, Colin Camerer again. Sorry, I'm talking a lot, but I want to totally endorse what Severine said about a meta-analysis. We've been working on some meta-analyses of what we think are very fundamental things, like what is the loss aversion statistic lambda, and commitment devices is it's right in the sweet spot, because the hardest thing about meta-analysis is if you have a lot of studies, and they're usually reported very differently. There's the non-standardization reporting, there's not much you can do about it. And if you're looking at things that cross different literatures like psychology or maybe clinical addictions and things in experimental economics, reporting standards are different. It's really, but if you have like 50 to 100 studies, and a lot of them are coming from one sort of reporting tradition, it's not that hard. You know, you hire a bunch of RAs to do it. It's a very good learning experience for like a first-year PhD student. You know, it's perfect. They have to really learn to read the literature super carefully. And even though I fear the meta-analysis are underpublished, they're always well cited, because people want to know, what's the deal with commitment devices? Are you people undercommitting, which is the kind of typical fear? Is it sort of close to half and half? It's more like in Margaret's thing. Is it, are there measurement questions about exactly what Severine mentioned? Because usually there's a lot of, early in the literature, there's a number of different methods people use, and sometimes the methods get a little bit more precise as you go along, so you can see a drift. You know, are there domain differences based on, you know, our teens and young adults, which is a lot of the non-weird college kids, versus older people or clinical populations, really the same. And meta-analysis is just, it's easier to do than ever because of internet, to actually do it. And you can email, you know, the ESA mailing list and say, does anyone have any unpublished papers on commitment devices? We really want your unpublished papers, because that will help us see if there's publication bias. You know, maybe a lot of people are finding, hopefully this won't happen to Margaret, but a lot of people are finding overcommitment, and it gets rejected by referees because it's like, you got the wrong answer, right? I mean, who knows? The best way to know is to compare unpublished papers or conference proceedings with publications and use some tricks. I think that's a fantastic idea. It's a little more
implementation. Yeah, it's like, how do you
yeah,
build
and
a team or like to do this? It's a lot of work.
It's in a way, it's more impactful than like 1 or 2 replications, and it's a lot easier. You don't have to produce new data typically. You just have to, like an audit, go and collect up people. You do have to be very methodical about how you code it, and you know, it's very hard work at a certain, you know, it's like writing a cookbook is hard work. And then if you're the checker who has to cook all the recipes 3 times, which is somebody's job, that's hard work too, right? But it's perfect for either like a pre-doc who wants, you know, that person at the end of a year or 2 will know more about commitment devices than anyone in the world. And again, it's like a chapter in a thesis potentially, or as part of a project. And I think the commitment device literature is at the absolute right point, where there's enough to work with, but there's a lot of open questions, you know. Please do it, someone on this call, or someone who knows someone on this call.
Absolutely, I'm interested. So if anyone else is interested too, let's do it.
Building a team, yeah.
Sounds good. I actually just saw a call. So there, I don't know whether you guys are on the ESA announce. There's a Google. It's a Google community. What is it called? Google. In addition to the email list, we also have a community on Google. So there was a call for the minimum effort game, I think.
Oh, yeah, yeah.
Yeah, from time to time you see these calls posted. Sometimes I miss it, but other times if I go there, I'll see, oh, you know, these are the unread ones. And yeah. So posting there is productive. Sometimes if I do that myself too. If I'm thinking that I'm missing literature, and just do a, you know, and you know, people have an incentive to do it because they want themselves to be cited. Yeah. And
yes, that's one of the technology ways in which the technology has really helped us. And I mean, again, I actually am working on that one a little bit, helping Taya Mai and Fabiana Tufano on the weak link games. But if you have what you think of as a failed experiment that's kind of written, it could even be a bunch of slides. Your experiment is suddenly very valuable, right? Because what's unpublished,
absolutely.
If there's just enough detail in there, it could even be, you know, you send us like raw data files accompanying your talk. You know, suddenly the thing that maybe the literature didn't like for a particular reason, called publication bias or whatever, that, like, it's like that trash becomes treasure, you know? So don't be shy about that. Sometimes in a smallish literature, it may even be 5 or 6 working papers, you know, that all go in the kind of the wrong direction, are extremely informative.
Yeah, we also, I think in the experimental economics community, there's a really good norm about data sharing these days, data and code sharing. You know, in the last 20 years, I don't remember a single case where I asked someone for data and didn't get it. So, yeah.
Yeah, and actually that's something to be, you know, I mean, we're among peers, but I think the code sharing, other than maybe computer science or something, the data and code sharing is very impressive. I mean, for some people, it has been for a long time. Like Hugh Mandrioni, I know, has put a lot of data on the web, and other people have been real pioneers. But and now it is really a norm. It's like, you better have it. And think about it in the process of when you're collecting your data and analyzing yourself is the best time to have it all put together, you know, beyond pre-registration and what have you. It's not going to get easier.
Yeah, so the one at, you know, the AEA has moved its entire data deposits to OpenICPSR, and it's one of so right now, before, you know, when a paper is accepted for publication, I usually just work with my co-authors to move everything up to OpenICPSR. It's free, it's maintained by professional archivists, and so and then just put a pointer there in your paper. It's super easy.
Yeah, I mean, it's easier. The people who have done these, like OSF is another one, they knew they wanted to remove all the like stickiness and pain points. Like, they don't want people to say, well, I looked at the site and you have to fill out this long form, and so I therefore decided to never share my data ever again. And some of it is, it's easy for an old person to say, but the first and second year PhD students and third year students, if they're working on helping you as RAs and so on, it's really, there's going to be like the first generation that's really has good data hygiene, you know, and I want them to look back and say, you mean you didn't like post all your data a couple weeks after you collected it? Like, really? Did people do that? Like, yeah, kind of. Right. So if, you know, it should be really built into the acculturation and how people think about data. It's going to be so useful moving forward.
Yeah, I mean, I've been wondering about, you know, this even being part of our training. I mean, you know, there are a lot of things I'm wondering about, but like, I think this is something that we shouldn't be taking for granted. I mean, the number of times also even just I blame myself, you know, thinking about my past self, who didn't think about my future self, about being able to redo files, and, you know, so I think these things are really, really important and should be incorporated in the way we teach.
Right. I think the journals are all catching up. So after the AEA journals, now Econometric is doing it, and the QJE. So I think eventually management science is doing it. So everybody will catch up. Yeah. So it will be enforced. Yeah. So we're very close to our close of party time. So the series is over. This is the last iteration. And the one of the organizers who's not here, but who really pushed for it, is Ted Turosi. And you know, when the New York meeting was canceled, Ted really pushed for having our junior faculty members, you know, giving our junior faculty members a forum to discuss their work, to publicize their work. And then we also asked our mid-career and senior colleagues to be the discussants. So for those of you who don't know, we asked every presenters to have a wish list. So, and then we basically just follow their wish list to invite discussants. And I've been really touched by how many people said yes, you know, from getting up at 7 a.m. like our Californian colleagues. And we even have a case where, you know, a colleague in Australia stayed up till midnight to discuss. So we thank everyone and for participating, for presenting, discussing, and we hope to see you in the global meeting, global virtual meeting, which is very exciting. So thanks everyone. Stay safe and have a wonderful fall semester.
Thank
Bye.
you all.
Bye,
Thank you
everyone.
So much for organizing this.
Bye.
Awesome.
Yeah,
Thank you. It was great.
it was fun. It was fun running it. Yeah. Bye-bye.